The general theory of information, GTI, provides a means not only to understand how information processing provides the cognitive and autopoietic behaviors exhibited by the biological systems but also provides a path to infuse these behaviors in digital automata. This video is a companion of the paper The General Theory of Information, Digital Genome, and Medical Knowledge-Driven Digital Assistant by Patrick Kelly, Francesco Coccaro, and Rao Michelinini. GTI and the tools that infuse these behaviors in the digital automata are discussed in several papers and books referred to in the paper. The picture shows the human genome and the digital genome and their roles in specifying and executing life processes with a goal and purpose in the physical and digital worlds. The essence of GTI is the relationship between information and knowledge and how biological systems use their cognitive apparatuses and mental structures to create or update knowledge from information received through their senses. Using GTI, we can derive a schema and operations that provide information processing architecture in terms of observations carried out by the cognitive structures. The references shown here describe the theory and practice of GTI and how to implement the structural machines and knowledge structures to infuse autopoietic and cognitive behaviors in digital automata. This POC is designed to show the implementation of the digital genome using a structural machine that operates on a knowledge network created using the medical knowledge derived from many sources including the large language models. The Autopoietic manager is implemented using Kubernetes and containers. The cognitive manager provides the workflow management of the information flow across multiple autonomous digital agents executing the cognitive functions of information processing, knowledge acquisition, managing the digital replica of the entities, relationships, and their state evolution history. The picture shows the implementation of the structural machine and the knowledge structures using symbolic computing structures that execute algorithms. Digital neural networks in deep learning are also algorithms implemented using symbolic computing structure. The paper describes how we use the knowledge derived from information carried by various sources to create a digital model of a process to assist both the patient and the healthcare provider with shared information. The goal is to reduce the knowledge gap between various parties to make the right choices in the early diagnostic process. It replicates the process, which humans use to create medical knowledge in their brains and use it in managing their health. The knowledge is derived from various sources shown here and a schema is created that describes various symptoms, diseases, patients, healthcare professionals, their relationships, and their actions in the early diagnostic process. The digital genome describes the process of processes involved, the resources required, where to get them, how to create the knowledge, and how to use it to assist the various actors make the right decisions using the right information at the right time. This picture shows various modules and the tools used to implement the digital assistant. The developers use functional requirements, non-functional requirements, and various policies that use best practices based on history and knowledge from various sources including the patients, healthcare professionals, and medical knowledge. The schema provides the long-term memory of the system state and its dynamics for various modules to derive the results they require to address the issue they are pursuing. A patient can ask which specialist would be needed to get consultation given the symptoms. Healthcare professionals can derive differential diagnosis of potential diseases given a set of symptoms based on the medical knowledge that is up to date. The purpose of this POC is to demonstrate the way to implement the digital genome-based digital assistant with autopoietic and cognitive behaviors. What you will see: distributed computing nodes deployed and managed by the Autopoietic manager that assures the stability and safety of the knowledge network. The cognitive manager manages the information flow in the system to execute the life processes where the nodes communicate with each other using shared knowledge that contains the digital replica of the domain-specific system with a schema and various instances containing various entities, their relationships, and their state evolution as events change the system. The processes that constitute digital assistant use information from various sources, relates the patient's symptoms, potential diseases, and possible specialists that can assist in further diagnosis. The information is updated in real time to keep the history of the system up to date. The patient and the healthcare provider use the digital assistant in their decision-making process with the right information at the right time.
My name is Patrick Kelly, and I'm here to present the digital medical assistant that is ran on the digital genome. The first part in initiating our digital genome is to start the cognitive network manager. The cognitive network manager acts as a central clearinghouse that relays data from our long-term database to our edge cloud systems. Each edge cloud system is deployed to the nearest cloud system that is possible for a user to run on. And the user interface we'll be using today is a simple React Native application. So now, as our application is initialized, it reaches out and finds the nearest cloud network by analyzing the user's IP as well as the user's ping to find the nearest cloud network to verify the lowest latency possible for an end user's connection. So within our database, we already have a user, and our user can simply log in through any amount of verifying details. In this case, we use a simple email and a password. Now, as our user is logged in, their independent information is put into a short-term database within our Edge Cloud server. This short-term database is used as a reference for any queries that are then sent to our cognitive network manager. So in this case, we have our user profile, which shows the patient's past history, as well as other identifying information, whether it be the patient's name, height, weight, or whatever other information may be useful in the diagnosis process. So our user is feeling some symptoms. So they go to our symptom input form, and they can simply enter in each independent symptom they are feeling. So in this case, our patient is feeling a cough, they're experiencing loss of taste, and shortness of breath. Now each of these symptoms will then be logged into our database as they are processed. As this form is submitted, each of these symptoms gets sent through our cognitive network manager, where it is assessed through several different methods of data collection and ran through an LLM to compile a short description of the hypothesized diagnosis. In this case, we see that our patient has been diagnosed with COVID-19. Now, in our background database, we can see that as the patient entered each symptom is recalled on the database and represented as an independent vertex. Now each of these symptom vertexes are able to connect to an independent disease vertex based upon the hypothesized diagnosis. So in our short bio, we see that we have the possible diagnosis of COVID-19, and COVID-19 is represented as its own independent node with its own attributes and variables. And we can see that each symptom is indicative of COVID-19. So now our patient is empowered to take the next necessary steps in the medical process to seek care and get a proper diagnosis. And the process of a care provider running through a decision of a differential diagnosis. So as our care provider logs in, they're met with their provider profile. So through their provider profile, they're able to select a patient that they are seeing through putting in their medical record number. And once they submit, this provider is now connected to this patient and is treating this patient. So, as our doctor is treating this patient, he notices the patient explaining several different symptoms. Those are bone pain, fatigue, loss of appetite, constipation, frequent infections, and weight loss. So now that all these symptoms are added, our care provider can submit these symptoms into our cognitive network manager, which takes into account all these symptoms and reaches out to several different data collection processes, including a large language model, in order to compile the possible diagnoses in a succinct and comprehensive report for the provider to view. So in this case, there are many diagnoses that could be possible by the symptoms, but our system believes that the two most possible are cancer and multiple melanoma. So we can see through our database, our patient has been connected with each of these various symptoms. Now, through this process, our care provider believes that the patient is suffering from multiple melanoma. So he goes and inspects the possibility in where the correlating symptoms with multiple melanoma will be shown to the provider, where he can then question the patient to see if they are experiencing any other symptoms that are matching with the possible diagnosis, as well as any of the correlating statistics of each symptom to the possibility of that diagnosis. So in this case, our care provider is fairly confident that the patient is suffering from multiple melanoma, so they decide to officially diagnose our patient. So through the process of diagnosing our patient, both diseases have been shown within our database. However, through our care provider, only the related disease of multiple melanoma is related back to our original patient. Therefore, being able to handle a process of differential diagnosis and creating a digital assistant for a process of early medical diagnosis. Thank you for your time.